Hello everybody, I'm Christopher Diekmann from Karlsruhe Institute of Technology, and I'm going to talk about stable water isotopologues from remote sensing and how they can support tropospheric moisture studies. If in a water molecule a single hydrogen atom is replaced by the heavier deuterium atom, then the stable water isotopologue HDO forms. As this leads to an increase of the molecular mass and binding energies, HDO evaporates slower and condensates faster than H2O. This creates differences in the atmospheric distributions that are both detectable from space. A valuable way for analyzing stable isotopologues in water vapor are two-dimensional scatter, as shown below. Here H2O is on the x-axis and the y-axis indicates delta D. That represents the standardized ratio between HDO and H2O. Depending on the chosen geographical regions, different processes dominate the tropospheric moisture and therefore generate different signals in the H2O delta D scatter. However, as different moisture processes typically overlay each other, a direct attribution to isotopic pair signals is still a major challenge. To add progress to this issue, we have developed a quasi-operational processing chain to efficiently retrieve H2O and delta D among other trace gases from IASI spectra and created a multi-annual dataset with a global coverage twice per day. To demonstrate the wealth of data, below we show an illustrative time series of H2O and delta D for the Sahel in West Africa for 4.2 km and their scatter for 4 different months. Here we use probability density functions that each summarize 90% of the respective scatter points, for instance the blue one for the February data and red for August. On the left we observe a clear annual cycle in H2O, but what is not reflected in delta D. In the PDFs we even observe a decrease of delta D when H2O increases during the summer months. To analyze this depletion in delta D, we use data from an isotope-enabled atmospheric model and calculate backward trajectories for the Sahelian troposphere. As shown here, the trajectory of sorbel reproduces the dominant transport pathways that contribute to the troposphere over West Africa. However, now I will focus on 3 characteristic trajectories. The individual isotopic evolution along the pathways is shown here in these 3 scatter plots and is color-coded for moistening, drying and condensation processes. The gray lines are theoretical curves calculated for idealized processes, in particular for air mass mixing, Rayleigh condensation, and for processes that go beyond the Rayleigh condensation, the so-called super-Rayleigh area. In extensive analysis, we added meteorological parameters like relative humidity, temperature, cloud particles, and were able to attribute those colored parts to effects of individual moisture processes in agreement with the corresponding theoretical curves. Moistening due to boundary layer mixing, drying due to large-scale subsidence, convective rain condensation, and rain evaporation. In statistical studies that are not shown here, we could give evidence that these theoretical process curves are not only representative for these single trajectories, but for the whole ensemble of backward trajectories for the Sahel. So, using these results, we can now try to understand the control mechanisms of the moisture in IASI measurements over the Sahel. For instance, the winter months over West Africa are typically very dry and depleted due to large-scale subsidence, what is clearly being reflected in the blue contour. On the other hand, during the moist summer period, the convective activity takes over and leads to moister but also to more depleted values. This can also be observed during the West African monsoon in the middle plot and also on the right plot. Here, the IASI observations during the monsoon are clustered according to precipitation datasets in non-rain and post-rain events. In all 3 plots, the PDFs are pulled towards the super-Rayleigh area, where rain condensation and evaporation are the major drivers. Therefore, these signals are a result of the increased convection during the West African monsoon, where heavier rainfalls lead to more depleted isotopic signals. To conclude, this process analysis therefore strongly supports to understand what controls the isotopic composition of observational datasets. Here, for IASI observations over West Africa, we could identify dehydration due to large-scale subsidence during winter in moist convection together with rain condensation and evaporation during the summerly monsoon as dominant control factors. All in all, the use of isotopic information can add strong progress for quantifying the individual branches of the hydrological cycle in the atmosphere. Thank you very much.